We just defined flow to be the path integral over a curve C through a vector field. In this video, I want to define flux. Let C be a smooth, simple, closed curve. So before we just needed a smooth curve, now we find out it needs to be simple and closed, and we need to talk about what both of those things are in a moment. Let C be a smooth, simple, closed curve with parameterization R of t, with t between A and B. And let F be a vector field, both of these things in the plane. My vector field is continuous over a region that contains this path C. Let N be the outward pointing unit normal vector. That's not necessarily big N. Remember, big N could point inwards or outwards. The principal unit normal vector at this point points inwards, and I need little n to always be pointing outwards. We'll talk about that in a minute too. The flux of F across C is this path integral, and what you'll notice is the difference between flux and flow is that the tangent direction has been replaced with this outward pointing unit normal direction. And we're going to need to figure out a way to calculate that, and we're going to need to talk about what it does. But it really is doing the same thing that flow's doing, just outwardly rather than around. All right, so now let's pick up the terms simple and closed. So I've given us a little table here, so I want to talk about these things by example. So when I say simple, I mean a curve that does not intersect itself. So this curve is simple. All right, well, what do I mean by closed? Well, I mean a curve that begins where it ends. So let's see, right here I've chosen the closed, so I need to draw a curve that begins where it ends, right? Starts and stops at the same point. But I'm also choosing the not simple part. So simple means it doesn't intersect itself, so here I need to draw something that begins and ends in the same place, but intersects itself. So that'll work. That is closed, but not simple. All right, well, let's draw something that's not simple, so it's going to need to intersect itself, and not closed, so it can't begin and end at the same place. Well, I think I know how to do that. That's not simple, nor is it closed. And then finally, the curves we want. We want something that is both simple and closed. Doesn't intersect itself, and it begins and ends at the same point. That is a simple closed curve. Now we also need them to be smooth. Now fortunately, it looks like this is also smooth because there's no sharp points anywhere. It's continuous and differentiable everywhere. And so I have a simple closed smooth curve in the plane here I've called C, and we can imagine a vector field. This time I didn't draw all the little vectors going around it, and we just need to talk about a way to get at this calculation. Well, that's all about figuring out what little n is doing. So let's remember something about flow first. One of the ways in which we can evaluate a path integral is this way, which has already done the dot product in there for us. So m dx plus n dy is what results when I do the dot product. And let's just think over here about that integrand, the dot product of f dot t ds. I do that dot product and I can write it down this way. So I want to talk about what to do if I replace t with little n. And the first step is to actually learn a little bit more about little n. So let's imagine that simple closed curve in the plane. Let's put a direction on it. Let's imagine that we have some x-axis and a y-axis, some axes. And then, well, I kind of know what big T would do everywhere, right? It's a unit tangent vector, and little n is a unit normal vector, always pointing outward, not to be confused with big N. So what I realize is since I'm in the plane, there's a third vector I can imagine that's perpendicular to both of these, and it's k, right? The z-axis would be coming straight out of the board, and k would be a unit vector kind of hanging out right there. And so one way I could think about n is it's the cross product between t and k. And I need to even think about it in that order. It's definitely t cross k because the right-hand rule would orient that going in the correct direction. Well, I know what vector k is. That's the vector 0, 0, 1. And so now I need to think about what vector t is. Well, one of the ways you can think about t is as dr ds, the rate of change of position with respect to arc length. Now, we usually calculate this as dr dt over its own magnitude, but this is something we saw earlier in the course, and you can actually, pause the video here and go verify that if you'd like. But now if I think of r of t as having a parameterization, that would be an x of t, y of t, and z of t, but then you go, wait, Bob, this was in the plane, that would actually make that, well, that's a 0 there. Okay, so dr ds, this would be dx ds, comma, dy ds, comma, 0, take a cross product. So to calculate n, we can actually just evaluate this cross product. And so just setting up my cross product here. All right, I'm going to expand across that top row the way we usually would. So my I component will be dy ds. My j component will be minus dx ds. And then, fortunately, the k component is 0 because this vector was supposed to live in the plane, right? It's outward pointing in the curve and lives in the plane, so we do end up with a 0 k. So now we know that little n is a nice vector dy ds minus dx ds and comma 0, and since I know I live in the plane, I'm just going to write that 2D vector down. That is what little n always is. Now fortunately, I can compare this to what big T would be. That's dx ds comma dy ds, and I see what's going on here, right? I swap the ordinates of big T and make one of them the opposite, and I get a perpendicular vector. The calculation we just did tells you why this one's the one we take the opposite of to make it be the outward facing unit normal vector. Okay, so now we're ready to actually think about what this calculation would look like. Flow, right, was this, and we're in the plane now, so we can get rid of the k component, where big T was dx ds and dy ds. And so now we know that to get that same kind of formula, I just need to think about dy and dx being swapped with the second one being a negative. And there's a formula I could actually use to calculate the flux. And we're going to do that in our next video.